Hello, can you hear me? Hello, hello, testing. Can you hear me loud and clear? Hello. Hi everyone, can you hear me? Audio is good, great. Thank you very much for confirming. Okay, let's just wait a few seconds and we'll start. Hello, Cosmic Lettuce from Arizona. And everyone, Larry, Ryan, DPI 209. The audio is good in Austin, good to know. Okay, great. So, hello, Peter, Guido, everyone. Let's get started. All right. Hello and welcome to the Daily Space for Thursday, June 21st of 2018. I am your host, Dr. Andres Plazas, and as always, we're going to bring you a run-up of today's news from space and astronomy. By the way, happy solstice of June to everyone. Either summer solstice or winter solstice, whatever you are on Earth. But let's move on to the news of today. And I'm gonna start talking about what we call the missing baryons problem. So what is that? I'm gonna talk about the composition of the universe. So I've told you guys that there's a lot of stuff that we don't know about in the universe. Dark energy and dark matter, that's about 95% of the contents of the universe. And the rest, the other 5%, is what we call the regular matter, and in cosmology we call that baryons. So baryon is a technical term from particle physics, but when cosmologists use it, it's a little bit more loosely, and they just say that everything we're made of, they just call it baryons. Like, you can think of it as regular matter. The thing is that you can predict from theory, from calculations, from the standard model of cosmology that we have, you can predict the amount of baryons that we should have. Like, out of that 5% of the total content of the universe, you should be able to predict the amount of that amount, and then you should be able to go and do direct observations and then try to figure out if your prediction matches the observation. And people actually tried, they got their prediction, and then they found out that after doing observations that there were about 40% of the baryons missing. So people were trying to add up to the amount of baryons that you could observe, like the luminous matter, and they couldn't find the rest. So this is what is called the missing baryons problems. So just to give a little bit more detail, the density of baryons, as I said, can be constrained using what we call the Big Bang nucleosynthesis. This is part of the Big Bang theory. It predicts the observed abundance of the chemical elements and how they formed at the beginning of the history of the universe. And you can also use the cosmic microwave background. You can use the changes in temperature that you observe in the cosmic microwave background, and then you can create your statistics, and depending on how these statistics behave, then you're gonna have a more or less amount of regular matter. From the CMB, you can also tell about the geometry of the universe, about the amount of dark matter, etc. But in particular, for this case, I can tell you about the amount of regular matter that we should find. But then on the other hand, from the observational point of view, the density of baryonic dark matter that can be obtained directly by summing up all the everything that you see. So okay, so everything that you see is what I'm talking about is the galaxies, and then the clusters of galaxies, stars, and these are relatively easy to see, so to speak. But then actually the large scale structure of the universe is like a cosmic web. So in between all these luminous galaxies and clusters of galaxies, then you find what we call filaments that are actually highly diffuse intergalactic gas, and also you have interstellar gas within the galaxies. So yeah, so astronomers, as I said, it was very hard to find, but they suspected that these missing variants were very hard to find, about 40% of the variants. But the astronomers suspected that the missing variants should be lurking in that place, in those places where the matter is less dense and therefore more challenging to observe, and that would be in the filaments between the cosmic web. So using different techniques, actually you can observe, you can try to get a better handle of this diffuse matter by using, for example, different wavelengths of the electromagnetic spectrum. And in this particular result that we're talking about today, the researchers actually used X-rays, used the XMM Newton X-ray telescope from the European Space Agency to try to find hot intergalactic gas. So what they did basically, and what you can see in this picture, is that they look at a source very far away, a quasar is what we call, and then you can see how the light of that quasar interacts with the matter in between, and they were able to find traces of certain elements, in particular oxygen, that they were lying there, and they just had the expected amount that the amount that we were expecting actually. So the researchers claim that we now are able to finally close the gap between in the baryon budget of the universe, of those missing baryons that we had. So they say that, of course, this is just the beginning, and I have another picture that I wanted to show that gives us a better idea. So just to back up a little bit, on the left is what I was telling you at first. Like, we have the total contents of the universe, which is the dark sector. You have dark energy plus dark matter. And then the remaining is what you call ordinary matter, or baryons in the parlance of cosmologists. And then that extra 5%, then you can divide that in another pie, and then that part, that yellow part that you see, was the missing part that the astronomers couldn't see, and then they were able to see now using X-rays. So they were able to identify this hot intergalactic gas that could make up to 40% of the total contents of the universe. So as I was saying, the researchers said that this is, of course, just the beginning now. So they are planning to study more quasars with this telescope, the Newton telescope and the Chandra telescope by NASA, in the coming years, to try, of course, to come up with a better measurement of this. So as you know, this would be like important news, but we need to take it slow and steady. Again, it's very important, but we need to do more measurements, and if it's possible, an independent a group of researchers should come and perform a similar measurement and confirm the result in an independent way. So this is, in a way, this is related to the next story that I want to tell, which is about dark matter, and one candidate of dark matter that is called sterile neutrinos. So recently, researchers from the Fermi National Accelerator Laboratory, Fermilab, located near Chicago, they have announced evidence for the discovery of the new kind of particle that is called the sterile neutrino. So if this is confirmed, this would be great news. It would be a remarkable breakthrough in particle physics, because if this particle exists, it could be a candidate for dark matter. So we were talking about regular matter in the previous story. We'll go back to talk about dark matter. And well, as you know, Fermilab, or you may or may not, Fermilab is the leading particle physics laboratory in the United States of America. And then came the Large Hadron Collider in Europe, between France and Switzerland. And then from the point of view of pure particle physics, like the highest luminosity, highest energy, the Large Hadron Collider now is the leader in the world. However, Fermilab is still doing a lot of good quality research, and now they have shifted their attention to do research on neutrinos. So neutrinos are part of what we call the standard model of particle physics. So I've talked about the standard model of cosmology, and now we have also the standard model of particle physics, and we call them a standard because they have been extremely successful. They have a solid theory, even if you need to come up with new components of the universe, like in the case of the standard model of cosmology. But what gives validity to these models is that they have been verified from the experimental point of view. So that's what we call standards. And the neutrinos, they're part of this standard model of particle physics. And there are three types of neutrinos that physicists they call families or flavors. It's just a name. But the basic point is that it was discovered in about 1999 or 2000 that one type of neutrino could be converted in another type of neutrino. So this is known as neutrino oscillation. And back in the time, it was a great deal because the quantum mechanics was telling you that if you could convert from one family of neutrino to another family of neutrino, that would mean that neutrinos actually have a mass, because before that, people were thinking that neutrinos were massless and they were traveling almost at the speed of light, or if they were massless, they would have been traveling at the speed of light. Okay, so we have that, and then people kept doing experiments, and then people thought that, okay, we have all figured it out. But they found out that there was an experiment called the liquid scintillator neutrino detector, LSND. This was an experiment that was done in Los Alamos National Laboratory, and they were studying this type of neutrino oscillation. And they found out with their results that they found, they only could make sense of these measurements if there existed a different type of neutrino family in addition to the three types of neutrinos that we know. And this is what is called what people call the sterile neutrino. And people call it a sterile neutrino because it doesn't interact in the same way as the regular neutrinos, which interact. They use what we call the weak force. So we know that in nature we have the weak force, the strong force, the electromagnetic force, and the gravitational force. But this neutrino would interact only through gravity. It wouldn't interact, so it would be a little bit different from the more regular neutrinos, and that's why they give them this name. So there was a follow-up experiment that was proposed, and it's called Mini Boon experiment, and it's located at Fermilab, and this is what the researchers are reporting this time. And they actually found results that are in agreement with what the Los Alamos experiment found many years ago. And furthermore, in the paper, they say that if you combine the data sets from the Mini Boon experiment and from the Los Alamos experiment, and then you do a statistical analysis, you would satisfy the criterion of what you call a discovery. In particle physics, there is a very stringent criterion to call something a discovery. The probability of that being only due to statistics has to be very, 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 very small. So there is a number, a quantitative criterion to say that something is a discovery. And so you might be wondering, okay, why aren't we hearing more about this? Because of course, if this is true, then maybe these people could win a Nobel Prize, I would say. But we gotta be careful now, because of course great claims require great evidence, or something like that, which is true. And the researchers, some of the researchers involved in these Fermilab experiments were also involved in the Los Alamos experiment. So that's already telling you that it's not an independent measurement, which is not optimal. You would like to have someone, you would like to have your rival group in science to find the same result as you found. You want to beat them, of course, but for the sake of science, you want to have the other people different from you do a similar analysis and find the same results, which is what I was saying in the previous story. So it could be actually these two experiments are like an exception to other experiments that have actually confirmed that there are only three types of neutrinos. So Could it be that these two experiments, they found something that the rest of the scientific community didn't find? That could be it. That's an option. Another option could be that they made a similar mistake, which could happen. It has happened. And then if they made a similar mistake, it resulted in a similar misleading result. So it is necessary that another measurement be done. So as I said, Fermilab has been focusing on neutrino research, and in the next decade they have plans for other experiments with funny names as usual. Now they have Microboon, they have another one called Icarus, or Icarus, like in the Greek mythology, and SBN, which I don't know exactly what that stands for, but the point is that there are different types of other experiments that are going to happen within the next decade to try to corroborate these measurements, which if it happens, that would be great. And yes, because we want to corroborate, either we want to corroborate our standard model of particle physics, which is awesome, but at the same time, it would be great if we could find something beyond that. And even if we find something beyond that, it would be great if we could find a candidate that could explain the dark matter of the universe. And then for the final story that I want to tell today, it's about testing general relativity using gravitational lensing, my favorite. So in this result, so these researchers, they used a galaxy that is relatively close to us, which is about 460 million light years, which that's close. But the point is that these researchers were looking for alternatives to the theory of general relativity. So this was a theory proposed by Albert Einstein in 1916, and for the past 100 years, general relativity has passed all the tests. So it's the most, it extended the theory by Newton, by extending the theory of Newton, then it became the fundamental theory of gravity, and it had passed all the tests that you can come of. But as I have said before, in cosmology we have this problem of the observed accelerated expansion of the universe. So assuming that general relativity is correct, then we would require a new component of the universe with negative pressure that would be causing this accelerated expansion of the universe, and then we just gave that the placeholder name of dark energy. But what is the other option? It could be then people are saying, well, general relativity, we actually have tested it directly only on solar system scale, so locally, so to speak. And it could be that on very, very large scales, which is where dark energy is acting, the largest scales of the universe, it could be that actually gravity behaves in a different way. And this is what people are calling modified gravity or alternative theories of gravities. So these researchers actually have been able to say that using, I'm going to explain this in a little bit, but by using this new technique, by doing this new measurement, they were able to extend a direct test of general relativity to scales, to galactic scales, like more than the solar system, and this is something that is done for the first time. So, as I said, these researchers looked at a galaxy that is relatively close to us, and because of that, we have two ways of measuring the mass of the galaxy. You can measure the velocities of the stars that are orbiting in the galaxy, and because of pure dynamics, because of the movement of the stars, you can figure out the amount of mass that the galaxy should have. But then, at the same time, if you have that the galaxy is this, that the galaxy is acting like a lens to a galaxy that is behind it, a background galaxy, and this is what is called gravitational lensing. Because the galaxy, the theory of general relativity tells us that it's distorting the space-time around it, and if you have a galaxy in the background and then you have an alignment, a geometrical alignment that is almost perfect, then the image of the galaxy in the background should be almost like a ring, which is what you can see in the image here. So this ring is called the Einstein ring, and then you can measure the radius of that Einstein ring, and then from gravitational lensing you can also figure out the mass of the system. And then you can do a little bit of algebra using the theory of gravity, and then you can say that the two masses should be the same, except for a factor. If that factor is 1, then that's general relativity. If we find a deviation from 1 from that factor, then we say that there is evidence for a mismatch, like there's evidence for something beyond general relativity. So basically what this study shows is like within the solar system, this factor is measured to a precision of 10 to the minus 5, like 1 in 100,000. So that's very well measured. But then the researchers were saying that previous studies were measuring this factor in galactic scales to a precision of about 20%. So it was 1, but to a precision of about 20%. And with this study, they were able to use gravitational lensing and the dynamics of the stars to bring down the precision of the study to about 8%, which is great and still big. It's still not 10 to the minus 5, but it's an incremental and significant advancement in the knowledge that we have. So because of the size of the Einstein radius is about 2000 parsecs. A parsec is a unit of distance that we use in astronomy. It's about 3.26 light years. Because of the size of the ring is about 2000 parsec, then you're able to say that we have tested the validity of general relativity up to those galactic scales. And yeah, they say, okay, the researchers say that this is giving support to general relativity, which in turn gives support to the standard model of cosmology that we have, the one that includes dark matter and dark energy. And yeah, well, the puzzle is there, but it's still a good measurement that we need to do. The more tests of general relativity, direct tests that we can do of general relativity, the better, of course. So now the researchers are going to try to make measurements in larger scales using more clusters of galaxies, and well, try to figure out if they get a consistent result. But okay, I thought it was a very interesting result, and I wanted to share it with all of you. So now I'm gonna see what. Okay, I'm gonna go back. Thank you all. Oh, okay. Yeah, happy solstice, everyone. Hello from Germany. Oh, that's awesome. Yes, I shaved. Thank you. You guys are observant. Hold on. There you go. Mhm. Is there any dark matter in the voids of the cosmos? So, by definition, there is significantly less dark matter in those voids than in the filaments and in the clusters that are like the knots between the filaments. So there is some, but it's not at the same quantity that you find in the actual scale structure of the universe, large scale structure of the universe. So yeah, that's why we call them voids. There is some, but it's significantly less than in the other parts of the cosmic web. Sterile neutrinos. Is any indication of any neutrinos from the alpha magnetic spectrometer at the International Space Station? I actually don't know about that, so yeah, sorry for that. I'm gonna check it out, but I don't know. I do know, and I think I mentioned this the other day, that there is some signal, some X-ray signal from a cluster that could be associated with the production of sterile neutrinos. And yeah, I was saying that I was talking with a colleague at Fermilab like a month ago, saying that he had the idea of maybe sending a detector in a cube satellite to try to figure out if this signal was consistent with the stellar neutrinos or not. But I don't know the alpha magnetic spectrometer right now, so sorry for that. We need a question icon. Yeah, that's true. That would help for me to try to identify. Yes, I'm scrolling back and trying to get them all. The Fermilab's holometer found a lower limit on the continuous nature of space-time. Do you know the lower limit? I don't know that one. I think it was much larger than the Planck scale. That would be interesting. I'm gonna actually check it out. Yeah, a few years ago I was in an interview at Fermilab and I had the chance to meet the person who was doing the holometer. And I thought it was pretty cool, but he was just starting his experiment. It was like 5 years ago or something like that. So I would be interested. I'm gonna look it up. I don't know if there are any results of the holometer right now, but apparently there are, Larry. So, well, thank you for the heads up. Sorry that I haven't checked that out yet. One parsec, 3.26 light years. Yes. Don't they use parsec as unit of time in Star Wars? I was like, okay. In one of those. All right, everyone. I don't see any more questions, but tomorrow we'll have Pamela again, so that'd be great. And well, thank you so much for watching. And this has been The Daily Space. It's a production of CosmoQuest and created by the Astronomical Society of the Pacific. So if you like the show, please give us a follow. That helps us a lot. Or even better, please consider subscribing. And yes, okay. So hopefully, well, we'll see you back tomorrow. And as you know, the Daily Space takes place every day at 1 p.m. Eastern and 10 a.m. Pacific and 6 p.m. London. Okay, everyone, thank you so much for being with me today. Bye-bye.